Hi, and welcome to another edition of Easy Theory. So today is going to be one of the big lecture days, and one of the reasons is this video that I've already done before on my channel, but I'm going to do it in more depth this time, is one of the most viewed videos on my channel by far, and a lot of people have personally requested for this particular video, so here we go. So what are we talking about today? We're talking about how to convert an NFA into a regex. So this blue arrow is what we did last time, and the white arrow is what we're doing today. Why would you want to do both of these? Well, this shows that NFAs represent all the regular languages, or they can recognize the languages, and so therefore, if we can convert back and forth in between these, then that shows the regexes recognize the regular languages too. So you can say that NFAs and regexes are the same in some sense, that you can represent a regular language with an NFA or a regex. So what we did last time was this blue arrow, which says you can convert from any regex into an equivalent NFA, and today we're going to go the other route. So the thing is, with an NFA, it can have any type of structure. So like, for example, I could have epsilon and A coming out of the start state, and maybe the start state loops on B, and then maybe this one comes down to here on C. This one will self-loop on A and B. This one's a final state, or maybe the start state's also final. Then maybe this goes to another state, and etc. So the structure of an NFA can actually be really complicated, whereas with a regex it was relatively simple. It was either one of these three base cases or one of the three inductive cases, and it can't be anything else. So in order to actually convert an NFA into a regex, well, we got to actually think of something more clever. Well, So the thing about an NFA is, of course, it can have any type of structure it wants, but maybe we can try to work with some really simple cases of an NFA and then try to generalize it to any NFA. So, and note, you could use a DFA with the method we're going to do today. I'm just going to use an NFA because it's more general, but you can certainly use a DFA here because every DFA is an NFA. Okay. So let's just look at a particular example. So this isn't really an example of the method, it's an example of an NFA. So for example, if we have, let's just say we have a single final state. Another thing here, you can always assume that every NFA always has exactly one final state. Put in the comments how you think you can prove that. Every NFA could have exactly one final state. So let's just say we have a really simple example of an NFA right here, which has two states. It has a start state and a final state, and this guy's not final, and there's only a single A here. Well, what is the regex that's going to represent this NFA right here? Well, pretty clearly, it's going to be just the single character A, right? Because this NFA does not accept anything other than a single A. It doesn't accept the empty string. Anything longer than a single character is only that one. Pretty cool. So let's do another slightly more complicated example. So here what we're going to do is I'm going to put an intermediary state in the middle between this start and the final state here. And again, I'm going to assume there's only one final state because we can always do that with an NFA. So here, what I'm going to do is I'm going to put A, B, and C on this. So what is the regex that corresponds to this NFA right here? Well, note that there's not, you can actually make infinitely many possible regexes for any. If you have a regex for something, you can make infinitely many more that do exactly the same language. So, and also put in the comments why you think that is. But the simplest one for in this particular case, you can probably see is going to be, well, the regex has to start with A no matter what, because that's what comes out of the start state. And then here, how do we represent B? Well, we can go around that loop 0 or more times, any number of times we want. So for regexes, that corresponds to doing the star operation. and then it ends with C. So what I think this regex is going to be is A, B star C. Okay, because we start with A, do the stuff around the loop 0 or more times, which is just what the star is. And note here, I'm not putting parentheses around the A and the B because I only want the star to affect the B here. I'm not affecting the A because the A is not involved in the self loop here. Okay, so then, and then it ends with C, of course. So then now let's make it a little bit more complicated. So then here, again, I'm going to have something, the same structure as before, but now I'm going to put a direct path, I'm going to label it D, from the start state to the only final state. Well, here we have to think a little bit differently because the NFA, whatever string it gets, it might take the top path here, or it might take the bottom path. So therefore, what do we represent OR with regexes? Well, that is the union operation. So here we can either take the top path, union, whatever the bottom path is. So that actually is going to be the same thing as before, which is A, B star C. But now we actually have to union the other path, whatever the regex is for the bottom path, which happens to be D in this case. Okay, so that's actually all that we really need here. But the thing is that as I'm going to start adding more transitions and whatnot, this is going to get considerably more complicated. So note here that in these examples, in every single one of these examples, nothing is coming into any of the start states here. And nothing is ever leaving the final state, which in an NFA, it very well could. So let's actually prove some things first. So we can always assume that an NFA has exactly one final state with no outgoing transitions, and even more than that, and the start state has no incoming transitions. I know that's a lot of text, but the thing is, this actually makes the NFA considerably simpler. So let's just imagine that we have an NFA right here. It could have any structure it wants. So maybe this has a start state with transitions coming into it, and let's say has 2 final states, and some of them have outgoing transitions. Okay, what could I actually do to this NFA that has these properties right here, has one final state with nothing leaving it, and a start state with nothing coming in? Well, the start state is pretty easy to do. It's basically the same starting part as the star construction that we did before, which is we're going to make a brand new start state here, but it's not final in this case, because if this state was final, then what we're going to do is we're going to allow ourselves to accept here. But either way, we're going to have an epsilon transition in. So then now this start state has nothing coming into it, and we don't change what we have accepted before because this is just an epsilon transition, and we just go right in. To handle the one final state with no outgoing transitions, it's actually kind of similar. But now what we're going to do is we're going to make a single final state out here, make all of the other final states no longer final, so these guys are not final, and we're going to epsilon our way from those previously final states. So that's kind of like the concatenation thing that we did before, where you make the first final states no longer final and you epsilon your way over. So we can always do this with an NFA, which is pretty cool. And So this actually makes our NFA considerably easier. So why is that the case? So what we can do is something similar to what we were doing in these examples up here, but rather do them down here and try to make the NFA simpler, simpler, simpler all the way down. And then at some point, we're going to make it so simple that it's going to fall into one of these three cases, which we know how to handle. Okay, so, and why can we assume this? Because actually we'll even go down to this case, which is it has two states, and of course those two states are the ones we just made. So we're going to make the NFA simpler by removing states. It's called the ripping states method. So how do we actually rip states? So what does it actually mean to rip a state here? Well, what it means is that we have we actually have three states, sorry. Any one of them can be final. I'm making them not final, but any one of them could be final. So here, there could be incoming transitions to any one of these, but we're not going to actually concern ourselves with those. So here, let's just call this first state Q1, the middle state Q2, and the last state Q3. So let's, in a different color, let's actually put the most complex scenario that could occur with these three states. So what could occur is we have an incoming transition, let's call it A, and a self loop on this, let's call it B, and a transition over here called C, and one that goes from one into the other. And you may be thinking, okay, this is not the most complex thing that could occur. Maybe Q3 has a transition back to Q1, or maybe to Q2, 2 to 1 or something. So we're going to only handle this one set or one path through the states at a time. So the state that we're going to try to remove is this one right here. So we don't like Q2. We're going to try to remove it at all costs. So the idea here is we don't want to mess up the rest of the machine at all costs. That's what we want to do. We want to make this as simple as possible, and any changes that we make should be local to here, between 1, 2, and 3. It shouldn't affect any other state whatsoever. It should only be local right here. So, and if we're able to successfully remove this, then maybe we can start trying to rip states in the rest of the machine until we get down to one of those really simple cases. So what are we going to do here? What I'm going to do is I'm going to make a copy of this big boy, and I'm going to paste it right here. So Q2 I'm going to try to remove. So maybe that there was this transition that came in and now is no longer going to a state, and we'll eventually handle that. But we're only focused on Q1 going into Q2, going out to Q3. We're only focused on that direction, so to speak. Well, what I'm focused on is how do I get from Q1 to Q3? Well, what we did before was we can either take this top path or we can take the bottom path. One thing I should note is we're focused on getting from Q1 to Q3 through Q2. So we're not focused on going, we're not focused on like going into Q2 and maybe it has a transition that goes out and then comes back in and then to Q3. We're focused on this right here, going from Q1 into Q2 out to Q3. So let's see, well, since we're focused on going from Q1 to Q3, well, we already have a way to get there. We already do. So what do we actually do about this part right here? Well, again, the regex that we had for this was A, B star C union D. So the D is here. Well, I can't actually represent that in the transitions yet. So this is where we're going to introduce a new type of object just for this purpose only. So what is this type of object is called a generalized NFA or a GNFA. So if you see GNFA method or something online or on one of my videos, it refers to this. So what does this mean? It means every transition is a regex. Why would this be useful? Well, if we did this ripping states idea and we go all the way down to 2 states like we had in the simple examples, then at some point we're going to have those 2 states with 1 transition between them, and if we do everything correctly, that a regex is going to be on that transition, and so therefore the corresponding regex is the regex on the transition itself. So if we, for example, in this case, we eliminated this state and replaced it with a single transition that was A, B star C union D, and that was on the transition label, then the regex is just what's on the transition label, which is pretty nice. So what do we actually do here? What we're going to do is we're going to remove these transitions just for now, just for demonstration purposes. When we do the example in the coming video, we're going to actually do a real example here. So here, what the transition label is going to, of course, be A, B star C union D. And so what we're really doing is we're simulating as if we went through Q2. Cool? So therefore, we're simulating as if we went through Q2 and maintain the other structure that was already there. The D transition was already there. Now, to handle the other case, now we need to make this more general. So how do we actually make this more general? So what I'm going to do here is I'm going to have a bunch of states over here on the left side. And I'm going to have S of them, for example. It doesn't actually matter. And I'm going to have a state in the middle called QRIP. Let's fit this on screen. So QRIP. So that, as you might expect, is the state I'm trying to take out. I'm going to have a bunch of other states, R1, R2, up to Rm, let's say. And I don't know if M is equal to S. In fact, it doesn't even matter. So what I'm going to have all of these Q states, the Q states are the ones that are going into QRIP, and of course there could be any number of them. But I'm going to have the transition for each of these be capital R1, then Q2 going in is going to be capital R2, and QS is going to be capital R sub S. So this is just a generalization of what we actually did before. Now, QRIP could have a self loop on it, or it might not, but let's just assume that there is, because it turns out we can assume that. I'm going to call it X, and the R states on the right-hand side are the ones that QRIP goes out to. So here, I'm going to call them T sub 1, T sub 2, etc., up to T sub M. So what we need to do is we want to simulate as if we're removing QRIP. So in fact, I'm going to temporarily remove it, but we see the rest of the structure. So now what are all the possible things that could occur? Well, you can be coming in from any one of the Q states into QRIP, take the self loop potentially, and going to any one of the R states. So let's just pick one of them. So let's pick one from each side, so to speak. Because we could be in any one of the Q or any one of the R states. So let's just say we were going from QI, we were originally going into QRIP. So what was the transition on this? It was R sub I, and we were going into QRIP. QRIP has X on it. So Ri could be a regex. X could be a regex also because we're dealing with a generalized NFA. Oops. Let me actually move this over. And then let's just pick R sub j over here. So state Rj. So I could pick any one of the Q states, any one of the R states. So this was T sub j. And potentially there could have been a transition to here, but if there was, we would just union it with whatever was there. And it turns out we can assume that there isn't one here, or if there is one, it doesn't actually matter. So let's actually try to rip it out. So let's try to rip it. And what are we going to do here? We're going to copy this. So I'm going to copy it. I'm going to remove Q sub rip. So then therefore the transition from Q sub I to R sub j will now be, actually I'll just remove all this and I'll make it red. So it would be R sub I because that's how we got into Q rip in the first place. Take the self loop here, which is X star. Probably not the best name for the regex. And then T sub j out to the state Rj. So T sub j. Okay, and then now what we do is repeat for all I and j. Because we could be in any one of the Q states or any one of the R states. And so therefore what we're going to do is just process all possible pairs and then add the transitions into the machine and then just repeat. And we can show that this is correct because if we look at any one of these, so we can prove it this way. So suppose that we were taking this transition in the reduced GNFA, this one right here. Well, the only way that this could have happened in here was that we went into Ri, took the X transition, and took the TJ transition. But that's exactly what this regex is. In the converse, if we went from this state into Q rip, took this transition, and took that transition out to R sub j, well, that regex is covered right here. So we actually will simulate the exact same machine, just more simply because we have one fewer state in total. And that will work regardless of which Q state or which R state that you actually picked. So now what we have is a generalized NFA, which has one fewer state than it did before, and it recognizes exactly the same language that it did. So now all we need to do, finally, is to repeat ripping until only the start state and single final state remain. And we can assume that this works because we're not changing the language at any point of whatever machine it was. And then now we're just going to have a single regex on the transition. And so we can assume without loss of generality, the final GNFA will be of the form start state goes to a single final state. Maybe I'll make the start state a little bigger. And it has some regex on it. I'm going to call it R. We can assume that it is like this because there's no incoming transitions, no outgoing transitions of the final state. And why can we be sure of that? Because if we look at this construction that we did here, we're only adding transitions that go from the left side to the right side. So we're never adding a transition that goes out of one of these states on the R side, and we're never adding a transition that goes into the Q states. So we can be assured that we will never add a transition that leaves the final state because there was never a transition that left the final state to start with. Same thing with the start state here. So we can assume that we can have a GNFA at some point with some regex on it that will have a regex, and therefore the language of the machine is described by this regex right here. Okay, so that's actually pretty nice, but we can actually assume even more things. So let's actually prove a different theorem, which is actually not shown very often, but I think is actually pretty nice because it allows us to work with regardless of what the NFA is. And what is it? It says if there is a missing transition, let's just say from Q, it doesn't have a transition to Q prime in the original NFA, because of course not every NFA has to have a transition from a state to another state. So if we're missing a transition in the original NFA, and note here, not the fixed one, so not the fixed NFA, but the original one, then what we can do is we can add this transition into the GNFA. And what is that transition? We can add the empty set transition from here to here. I can't add the empty string transition. I can add the empty set transition. Why can we do this? Well, let's actually think about this. So why can we actually do this? Well, the only possible cases are when we're looking at the, I'll just do a proof here. So let's just say we have this case right here, which is we had the Q sub I state taking the R sub I transition with an X on the self loop on Q rip, and then takes the TJ transition to Q sub J. So the first case is when T sub J is the empty set, which is certainly possible. If we're adding a transition like this, we could be adding it right here potentially. So what do we actually do here? Well, the reduced transition will be Q sub I goes to Q sub J, which is R sub I, just doing the recipe, X star, and then the empty set, because T sub J is the empty set. Well, note here that the empty set is concatenated with the rest of the regex right here. And so therefore, if you concatenate the empty set onto anything, you will get the empty set. So this thing actually reduces to the empty set. And why does this work? This says that Q sub I cannot reach Qj through Q rip like this, because there's no transition here. Well, now this says Qi can't reach Qj anyway, which is exactly what we're doing right here. So therefore, we can assume it in that case. And it's exactly the same thing if R sub I is the empty set. It's the exact same idea. It's just that the empty set's on the front instead of on the end. But you still, because it's still concatenated with it, you will still get the empty set. The only other case is when the empty set is the self loop. So let's actually handle that case. So I'm going to actually copy this so I don't have to redraw it all. Copy, paste. So then now I'm T sub J might be non-empty, I don't actually know, but I know for sure that the X right here is empty, which actually represents there's no self loop on Q sub rip, which could happen in the original NFA. So what does the reduced NFA look like? Can I actually paste? No, I can't. So I'll paste this again. Copy, paste. So then now Q sub rip is gone. Actually, I didn't even have to do that, but anyway. So then this represents R sub I, which might be non-empty, empty set star, because we're doing X star, well, X is the empty set. So empty set star, and then T sub J. Well, what is the empty set star? Well, you can actually prove that empty set star is equal to the empty string. And that's actually kind of surprising, but it comes directly from the definition. So what this is equal to is r sub I t j, because if you concatenate something with the empty string, then you just get whatever you had before. Well, that works, that makes sense, because if there was no self loop right here, we can just go straight through and there's no self loop here, which is exactly what this is representing right here. So why does this matter? Why should you care about this? Well, here, I don't have to, if I'm trying to implement this, I don't have to think, is there a transition between this state and this state? Because what I can do is I can just add a transition if it's not there, and then therefore I can be assured that it is always there. So what are we actually really doing here? What we have is a start state that that might have an epsilon transition to a state. Well then, let's just say we have a bunch of states right here. Well, they're all going to have a transition in every direction right here. So every single state is going to have a transition. Actually, they're all going to have self loops too. Some of them might be the empty set. But at some point, we're going to have the empty we're going to have these outgoing transitions to the single final state. But again, we're going to have self loops on every single state here. And this structure is what is called a complete graph, although it's not really a graph, but you can think of it as being complete because every single transition is present. And so now I can implement this a lot more simply. Cool. So, my God, that was 32 minutes. So thank you for your patience if you were able to sit through all this. Leave into the comments if you found a different way to show that you can convert any NFA into a regex. There are other ways you can do it, by the way, but you can actually show that you can convert any NFA into a regex. And so therefore, that shows that regexes recognize exactly the regular languages. So after all this, thank you for your attention. If you have any other interesting ideas, please put them in the comments. I read every single one of them. I respond to all of them. You can also join our Discord server and a bunch of other links in the video description, such as our Patreon if you want to contribute. Otherwise, please like and subscribe to the channel. It also really helps. And as always, I'll see you next time. Thanks.